The Upright Robot by Parker Bolick, Charlie Bouchillon, Heather Riley, and Selyna Gant. When we were told to start this project, we had to create groups of 3 or 4, so eventually we all talked together and decided we could do the Upright Robot, as this was the project that piqued most of our interests. Our first plan of attack was to read up on the project and to find any resources we could to help build and learn about this type of robot. Our goal was to design and implement a feedback control scheme to control a simple robot that could maintain itself in an upright position using feedback control. The general form of the robot was a tall, narrow box with 2 wheels at its base. We used the principles we learned in class to design a controller for the robot, which could stabilize the robot's position at a set point. Because of the robot's narrow base and highly unstable shape, our control scheme needed to operate without a lot of overshoot or oscillation, which could cause operation failure. We theorized the robot would only be able to stabilize within a certain range of tilt from the vertical. We also wanted to avoid any steady state error. The team agreed that the robot needed to be perfectly upright, at least to such a degree that the casual observer could not see any error. These constraints led to the selection of a PID controller scheme, that is, a proportional, integrative, and derivative control. Having each of these components should leave a stable system if the gains are all correctly adjusted. The starting place for pole adjustment should be based in theoretical calculations and then be adjusted based on trial and error experimentation. The best way to do this would be to find the closed loop transfer function and then the poles of the system. For the system to be stable, the poles would need to remain in the left half plane of the imaginary real axis. That is, the real component of our poles needed to be negative if the system is to remain stable. A Ruth array can be used to calculate constraints for each of the gain values as an additional guideline. For the physical setup of the robot, our team was primarily concerned with cost and simplicity. Our budget was tightly constrained and none of us were particularly experienced in the creation of a robot. Our final list of parts is detailed in full in our report, but the major components were a set of wheels, gearbox, Arduino Uno, gyroscope sensor, breadboard, battery holder, and 2 integrated circuit replacers, all connected to a plate. Components were variously soldered, wired together, or glued in place. Assembly of these parts was easy once all the parts had arrived. We experienced some delay in assembly due to slow shipping speeds. The gyroscope sensor and integrated circuits were both wired to the breadboard and connected to the Arduino. A 9-volt battery powered the Arduino itself, and additional batteries were attached to the circuit to power the motors, which were also connected to the Arduino via the breadboard. Once we had a circuit wired, we needed to program the Arduino to code so that our system could actually run. No one on our team was particularly experienced with the type of coding needed to complete this project, so this was by far the most challenging component and caused significant delay in testing and experimentation. At first, we were unable to get the code to run. The Arduino and the sensor would turn on immediately when supplied with power, indicating our circuit was good, but the motor would not engage. After more than a week of worth of troubleshooting, we were finally able to get the robot to attempt to stabilize and begin testing. Because of our significant delays in testing, our team did not have much time to conduct extensive experimentation and control adjustment. It is clear that our robot did attempt to stabilize, though it massively overshot the set point and could not be left to operate on its own for fear that it would run off the table or break itself. With further testing, we expect to obtain an operational upright robot.